Dear students, today we are going to learn the applications of eddy current. What are the applications? You can have more than the terms, the cases which we are discussing right now. You can know more applications, but we are talking about the few of the main applications of eddy current. Now, the first application we will understand is what is damping the oscillatory motion. For example, let us say we want to make accurate measurement by a beam balance, and in beam balance what you have is you have a fulcrum, the rigid support, and two arms of equal length. Then we place something which is to be measured against the opposite end, which is having standard weights, and then we compare. When the rod becomes horizontal, we take that the weight of mass of that body is equal to that standard weight measurements. But if we want to have accurate results, the physical balance should be more sensitive. It means that a slight change or difference in the masses of the two arms of the beam exists. For that case, the index rod must swing. Now, if it is more sensitive, it will swing for a very long time before coming at rest. But that is not desired, because we want accuracy, but we can't have so much time allotted for waiting that index rod to come at rest and then knowing that which side is heavier, so that it can be further compensated or balanced. So therefore, we find an application of eddy current in this case, and we can reduce the oscillating time without compromising with the accuracy of the beam balance. How it is done? The index rod is fixed with a metallic sheet, and that metallic sheet is allowed to pass through the between the two poles of a magnet. Now what happens? Some eddy current is produced in the metallic sheet, and that opposes the motion. So what happens? Let us take the two situations while the sheet is entering the magnetic field. In that case, what you see, the magnetic field lines are of the magnet is from north pole to south pole. That means the magnetic field lines moving from left to right is getting associated with the sheet, and according to Lenz's law, what you know, that it will oppose the change, and that will be done only by producing some eddy current, which produces a magnetism which is such that it produces magnetic field lines from right to left. So that means the magnet is producing magnetic field lines from left to right. That is getting associated. It means magnetic field lines associated with the sheet is increasing in this in this sense that it is gaining magnetic field lines directed from left to right, and the eddy current will be such that it produces magnetic field lines directed from right to left, such that this change in magnetic flux associated with the magnetic sheet is nullified or opposed. So therefore, you can see here we have clockwise current, means this phase, the phase which is directed towards the south pole, directed towards us, as you look in the picture, is south, behaving like a south pole, and the opposite phase, which is not visible, behaves like a north pole, and that means north pole is repelled by north pole, and so its motion is slowed down. Now by some reason, if it is able to cross the magnetic field, the middle center of the magnetic field, now it starts moving out of the magnetic field. What happens then? In this case, now the magnetic field lines directed from left to right associated with the sheet is now decreasing, because it is moving away from the magnetic field, and that in that case again the Lorentz force the Lenz law will be useful to explain that it opposes this change, and therefore the eddy current will be produced such that the sheet produces magnetic field lines which is directed from left to right. To compensate this loss means it opposes the change, and therefore this phase which is seen by us means the phase which is directed towards the south pole of the magnet now starts behaving like a north pole, and that means it produces magnetic field lines directed from left to right, so that loss is being compensated. So that means this phase now starts behaving like a north pole, and here it is getting attracted by the south pole, so that damps the motion, it slows down the oscillation. So each time it crosses, the sheet crosses the magnetic poles, each time its speed is slowed down, and finally it comes at rest in no time. So that way we have done the damping of oscillatory motion to save our time, and this has great many applications in similar devices. Now we talk about second application, magnetic braking. Again the same principle is there. The wheels of the train, fast moving train, are moving very fastly. If you apply the mechanical brakes, the heat produced due to mechanical braking will be so high that it can even melt the wheels, it can melt the shoe brakes, so that application is not acceptable. Now then, how we can stop the train in such a high speed in less time? That is done by this magnetic braking. What is that it does is the magnetic sheet now is against the wheels are now made to exposed to magnetic field. Now moment the wheels are exposed to magnetic field, it produces eddy current, and that produces slowing down of the wheels without doing any mechanical braking. The concept is the same which we have discussed over here. Now the third one is induction furnaces. What is it is? Say for example we want to create very high temperature. Say for example if we talk about say nuclear reactors where high temperature is required in a very small zone where we have radioactive materials, and that we want to have nuclear reactions generated, started. So that means high temperature is needed, and then that is possible only if the area is kept minimal. If you have a larger area, much energy will be required, but that purpose will be very difficult to accomplish. But if we have a smaller area in which we have to generate high temperature, that is possible with less heat energy generated. Now so less heat is generated due to the flow of eddy current. And how we do it? For the small area we keep it in enclosure, and we expose it to the changing magnetic field. This changing magnetic field produces eddy current, and that produces large amount of heat in very small area. So our purpose of creating large heat and high temperature in a small or enclosed area, remote area, is possible. So this is the third application. Fourth one is in AC electric power meter reading. We use the eddy currents to make the measurement of flow of AC current drawn from the source. Now however we have now switched over to the digital AC meters which are based on semiconductor chips, and we shall be talking about semiconductors in the coming chapters. So these are the few main applications of eddy current, but eddy current can have so many applications in our life. So it is very important to have a good understanding of such topic. Thank you and have a nice day.